All right, well, that we have a reasonable number of people here. Line integrals. Picking up where I left off last time. Okay. Now, there are two formulas that I showed you for line integrals for completely different situations. And so in both cases, you're given a curve C that's described by parametric equations that are written as R of t as a vector value function, but it has components x of t, y of t, z of t. And t goes between a and b. So if your integrand is a scalar valued function, then it's written this way. You have your function f of x, y, z, often using a lowercase letter in textbooks, ds. So that's the way it's normally styled, but then what you actually evaluate is integral from a to b, f of, I'm going to write this two different ways. One in like all the components written out, and the other in vector form. So the square root of x prime of t squared plus y prime t squared plus z prime of t squared dt. Now in vector form, that would be the integral of little f with r of t, the parametric equations plugged in, times the magnitude of the tangent vector, r prime of t. So that goes in there. Okay, so that's the first one I covered, and just some examples off of that. The second kind that's really of greater interest to us is line integral of a vector field. Capital F, and I use a vector symbol here. And the notation I'll use is, this has components, which I'll name P for the x component, Q for y components, and then R for the z component if there is one. Okay. All right. So the line integral of a vector field is written this way: f dot, as in dot product, dr. So you can see how differently these are written, so you know which situation is which. And the integral you actually evaluate, so first in vector form, is f dot, f of r of t, dot product with r prime of t. So you can see the difference between here and here. Here we're just multiplying scalars or numbers. Here we're taking the dot product because both of these are vectors. And if I want to write that out in component form, then that would be P of x, y, z of t times the first component of this, which is x dx dt, plus q with your parametric equations plugged in, dy dt, plus r with the parametric equations plugged in, dz dt. Now I have not yet done any examples of that, but I'm about to. That's what today is for. Now, I'm going to point out one other kind of notation for line integrals of vector fields. It's something we're going to see quite often. Because here I have P times dx dt and then Q dy dt. So this can be written as the integral over the curve C of P dx plus Q dy plus R dz. So that's another shorthand for line integrals. So when you see this notation, the way you would evaluate this, like if I said, like on a homework or a test, what is the line integral of P dx? The way you would rewrite that to evaluate it is, you have parametric equations for the curve C, you plug it into your function P, and then dx means dx dt. And I'll be using this notation in examples, but I wanted to mention it up front. Okay. So now, okay. Do I have a wrong notes? Yes, I have a wrong notes. Okay. Be right back. Okay, so for our first example, so the curve C is defined by these parametric equations, t, sine t, and cosine t. So here we have, this is your x of t, y of t, z of t. And I actually use this curve or something similar to it as an example before, because if you look at the y and z components, sine t, cosine t, that's going to trace out a circle. But then the x-coordinate is t. So this is going to be a helix, it's going to be a spiral. It moves along the x-axis. And t goes from 0 to pi. So in fact, it's not really going to get to spiral. It'll start to do it'll trace out a half circle and then stop. Okay. So the line integral we'll evaluate is this vector field of x, y, z is given by z, y, and minus x. So in the notation on the other board, these are your three components, p, q, and r. Okay. So, so the line integral over the curve C of the vector field f, but I can also write that as integral over the curve C of p dx plus q dy plus r dz. And now I can fill in what your components p, q, and r are. So p would be z, q would be y, and r would be minus x. Okay. So that's how far you can get without actually taking the curve into account, just plugging in your vector field. But now we need to express everything in terms of t, and then we'll just have a single integral to evaluate. So at least there are no double or triple integrals in this case. Don't worry, you'll see those again later. Oh, speaking of integrals, you've seen the signs around the hallway. On Friday, there's an integration bee that the department is holding. And I believe the top three, people who place the top three will get cash. I think like $100 or something is the grand prize. This is sort of practice for a conference that's held every spring for the Louisiana-Mississippi section of the MAA, or Mathematical Association of America conference. And it goes back and forth between Louisiana and Mississippi. So next spring, this coming spring, is Mississippi's turn. I think it's going to be held at Millsaps. So they hold Integration B there, where you compete against the other schools. And last year, it was one of our own students that won it, which was highly unusual. So it's usually these high school kids from Louisiana, they win it every year, freaks. And there's then possibility for more prizes. So if you want to give it a shot, and I think it'll be mostly, if not entirely, single integrals. So if you're good near Cal 2, you might do well. Okay, but you can see the information, like there's definitely signs all through this hallway. Oh yeah, and pizza served, of course. Maybe I get some people to come. So that'll be on Friday, I think in the morning.
It's at 9.
What?
Starts at 9.
Yeah, like 9 to 11 or something like that. Okay, so it doesn't conflict with this class. Okay, now we're going to fill in everything. So, so we have, so x of t is t, y of t is sine t, z of t is cosine. So for dx, dy, dz, we need our derivatives, which are
1 cosine.
Yeah. Okay. So now we can take all of this and just plug away. So our limits are 0 to pi. Probably refreshing to have the limits given for a change. Enjoy while it lasts. Okay, so z is cosine, and then dx is just 1, so you're going to get dt. Okay, so, well actually what I can do is I can just fill in 1, so this is dx dt, and then I'll put a dt at the end. Y is sine t times dy, which is cosine t. So this is y dy minus x, which is t, and then dz is minus sine t. Okay, so it's minus x dz dt. So that's just where all the pieces are coming from. Okay, so now the integral is completely set up. And this is something that you can go ahead and integrate. Although, what would you need for this one, for this term?
Is that t times negative sine?
Yes, it is.
Okay.
So, okay, so simplifying, it'd be plus t sine t. How would you integrate that? What do you need to use? You learn how to do this in Cal 2.
Would you use substitution then?
Substitution won't help.
Split it up.
No,
No, you can't just mean t plus sine t.
not when it's multiplied.
Sorry, I thought it was a plus in the middle.
Oh. Okay, yeah. Alright. Okay. Alright, now that that's been cleared up. Other integration techniques? What?
What is that? Integration by part.
Yes. So if you integrate t sine t, you do integration by parts where this is your u and that is your dv. And you can go from there. Okay. All right. This example is worked out further on page 112. I'm actually behind, so probably should have yammered about the election. Where the integral is worked out there, and then the integral turns out to be pi. But as in the last chapter, I want to make sure people understand the setup. So any questions about the setup? Okay. Okay, here's another example where the vector field to integrate, I can do it twice, the same vector field, except for a curve will be different. So you can see how different kinds of curves are handled. So for the next example, this will just be a two-dimensional integral. So your vector field is sine x cosine y. So that is your p, and that is your q. We don't have an r because we're in two dimensions. And for the first curve that we'll do, this is the it's the top half of a circle, unit circle, x squared plus y squared is equal to 1. So sometimes a curve might be described using an equation like this, and you have to come up with the parametric equations. Now, this curve is actually going to be two pieces. There's the top half of a circle, and it's traversed counterclockwise from 1, 0 to minus 1, 0. And then, okay, it's actually getting two different curves at once. Then, on the line segments, from resuming from this point, minus 1, 0, to minus 2, 3. So what we can do is we can integrate this vector field over both of these curves, and then we can just add the results together. So the difference with, in the previous example, the parametric equations were just given to you. Now they're not, but here's how you can come up with them. So first, here's what the situation looks like. So we have top half of a semicircle. So we're starting at 1, 0, going this way counterclockwise to minus 1, 0. And then I'm going to call this curve C1. This is the circular part. And then the next segment, C2, goes from here to here. Okay. To the point minus 2 and 3. Okay. So what we can say is the line integral of this vector field over the entire curve C. So C is equal to the C1, the circular part, union C2, the line segment. So I can just write this as, and we're going in this direction, as an integral over C1 plus the integral over C2. But then I can write this in terms of components. So that would be integral over C1 p dx plus q dy, and then the same thing for the other curve. And then I can fill in what p and q are. So I have sine x dx plus cosine y dy for both curves. Okay. Now, okay. All right, so now what needs to be done in both cases is filling in the parametric equations for C1 and C2. Fortunately, there's not that much involved, but it is the sort of thing that you should be prepared to do, like in a homework or even a question on the comprehensive final exam that's coming.
And that last one right there, is it supposed to be cosine y dy?
Yes, cosine. Yeah, cosine y dy like in the other one. Oops. Okay. Good catch. All right. So let's just focus on C1, the circular part. So now what would be typical parametric equations for a circle? Because we've seen this sort of thing before, like when dealing with polar coordinates and things like that. We need x of t and y of t. So based on the experience you've had dealing with all things circles, what should x of t and y of t be? What do you think should be choice for those? Q minus the circle radius 1. I won't take a stab at it? It's okay if it's wrong.
Or he's describing a circle.
Yes.
Okay.
Yeah, or t, yeah. Yeah, cosine t, sine t. Now, the thing to keep in mind is, this not only will trace out a circle, but it will do it in the direction that we need. Because the problem specifies counterclockwise. So, alright, so that's what will happen in this case, starting from this point, so it's convenient. Whereas, for instance, if you did like x equals sine t and y equals cosine, that would also trace out a circle, and that would go clockwise. I'll say more about orientation later, but that's particularly important. So yeah, that will work, but we only want the top half, so what should t range over? Yeah. Okay. So now we have parametric equations for that. So the integral of, sine x dx plus cosine y dy is going to be the integral from 0 to pi of sine of, this is x of t, and this is y of t. So we have sine of x of t, which is cosine of t, and then dx, we need x prime and y prime. So once you come up with parametric equations, you might as well take the derivatives of them right away, because you know you're going to need them. So we have minus sine and cosine, and you can fill those in. So this is sine x dx plus, cosine y would be cosine of y, which is sine t, dy, which is cosine t, all dt. Okay. So now you can go ahead and integrate that. Now, interesting. Where? Here?
The dx.
Yeah, we substitute.
Sorry, that should be negative sign. Okay. Yeah, so whatever derivatives you have, go in here. Sorry about that. Any other setup questions? All right. So this is your dx dt, and then dy dt. So whenever you see in line integrals like a dx or dy, you can think of it as implied dx dt dt. That's what you'll actually be evaluating. All right. Now, actually, let me simplify this a little bit. So we have minus sine cosine t sine t plus cosine of sine t times cosine t dt. Now, one thing that I've noticed often is a certain scary mathematical illiteracy, if you will, because if I give it a function like this, like on a test, it might be misread as, instead of, like maybe this is sine t, cosine t, sine t, which this is definitely not. This is sine of cosine t, which is no different than like sine of pi over 2 or something like that. And that is multiplied by sine t. So be careful what you're reading at this point. Now, for evaluating this integral, it's best to treat the two terms separately. So I'll just break it up into two integrals. And that's a good rule of thumb anyway. It certainly doesn't hurt to do it. Sometimes, if you need to handle different terms using different strategies, you don't want to have them mixed up. Okay. So how would you handle this one? Actually, you can handle both of them in a similar way.
Use substitution.
Yeah, so what should substitution be?
You should be, like for the first one, you should be cosine.
Yeah, that's your u, and then du is sine t dt. Here again, this would be your u, and then that would be your du. Okay. So then what would happen? Now this is going to be
This is going to be a double substitution.
double substitution.
No, that wouldn't work. Never mind.
Okay.
Sorry.
Yeah, not necessarily in this case. So now what you have is sine u du for the first one plus cosine u du for the second one. Now, there are two ways to handle substitutions. You can either go ahead and change the limits now, like by, okay, so in this case we have u is equal to cosine. You can take your original limits 0 to pi and plug them in. And what would happen in this case is if you did that, you plug in 0 and pi into cosine and you get 1 to minus 1. And when you plug these limits in here, you get 0 and 0, which suggests that you're just going to get 0, which actually, that is what happens. Okay. No? Okay. Yeah, that is what happens. Okay. So, in fact, what you could do is you could just go ahead and write this one off right away. That's just going to be 0. What about the other one?
You can write it off as just
Neat.
a full period and it's an odd function.
Yeah. Well, it doesn't even have to be a full period. But yeah, odd function on a symmetric interval.
Oh,
Yeah, the limits are negatives of each other. So yeah, all of it is 0. Now, I don't know if this might have occurred to anybody. Okay, so that part, the circular part, is 0. I don't know if this might have occurred to anybody, but if we look back up here, you might have thought, well, if you just have sine x dx, integral of that, why not just integrate that? Because that's something you know how to do. Or same here, cosine y dy, you know how to do that. And the thing you have to think about, if you're going to do that, you have to think about what limits should there be. And I can actually answer that question. You could treat these as ordinary integrals as long as you choose the limits correctly. And in this case, the limits are equal to the because it's dx, it's x values. The starting and finishing x values. Here, the limits are the starting and ending y values. Well, what's happening with this circle? It's starting at this point, 1, 0, and going around the first top half to this point, minus 1, 0. So x is going from 1 to minus 1, just like you saw here. Yeah. And then the y is going from 0 to 0. And sure enough, those are the limits that we get. So you can do that. But that's only a good idea if these depend on one variable only, sine x dx, cosine y dy. Because generally that's not going to happen. Your integrand may involve both x and y, or x, y, and z. So I wouldn't recommend that case. But if you have a line integral that depends on only one variable, it does work to do that. Okay, so that could be a shortcut. Now that is for the that's for the circular part. For the other part, we have the line segment. Let's see, and I need to leave that up here. All right, how to come up with parametric equations for a line segment. We actually have seen that once before, but that was before the test. And now you guys are paying attention more, right? So for C2, that goes from minus 1, from this point to this point, your direction of your line segment I'll call V is equal to the end point minus the starting point. So that's going to be minus 2 minus a minus 1, and then 3 minus 0. So it's minus 1, 3. So that vector indicates the direction from this point to this point. So now your parametric equations, RT is equal to the starting point plus t times v, this vector v. And t goes from 0 to 1. So that's your standard approach that I used before to come up with parametric equations for a line segment. So what that means is, component by component, x of t is the x-coordinate, and times this coefficient times t. So it's minus 1 minus t. And then your y component, same deal, your starting y value to 0 plus t times this coefficient. So this is going to be 3t. So those are your parametric equations. And then, of course, your derivatives are very convenient. So dx is equal to minus 1, or sorry, x prime. X prime is equal to minus 1, and y prime is equal to 3. Okay. So now what you can do is your line integral, so it would be sine x dx plus cosine y dy. Now if you express this in terms of parametric equations, you get integral from 0 to 1 dt of sine minus 1 minus t times minus 1, so that's your dx, plus cosine of y, which is 3t, times your derivative of y with respect to t. Okay. So you can go ahead and integrate that, and this is done on page 114. But you, like I said before, you could use this, just integrate these directly as long as you use the correct limits. So for x, your limits would be from minus 1 to minus 2, because those are the starting and ending x values. And then for y, you'd be using from limits from 0 to 3. So So the other way I could write this is the integral from -1 to -2 of sine x dx plus the integral from 0 to 3 of cosine y dy. Okay. So you can just work it out this way. So then you'd have cosine x from -1 to -2. No, minus cosine x plus sine y with limits 0 and 3. And then you can plug in the limits and you're done. Okay, so any questions about this one? So if these terms depend on what, with a dx or dy depend on only one variable, you can take a shortcut, just use the starting and ending x or y values as needed. Otherwise, you can always do this. Fill in your parametric equations, fill in your derivatives like dx dt and dy dt. Then you have a single integral with respect to t, and you can just work that out. Okay. Okay. I have just enough time to at least do the setup for one more example, and then we won't be as far behind anymore. And the homework on this section is due next week. So you have a good amount of time. Okay. So your vector field has components p, q, and r is just z, x, and y. Your curve c, x of t, y of t, and z of t is equal to t squared, t cubed, t squared. So you might as well take its derivatives right away. Like I said, you know you're going to need them. So we get 2t, 3t squared, 2t. And t is given to run from 0 to 1. So as far as your setup goes, the line integral over the curve c of f, which is the same as p dx plus q dy plus r dz, which is the same as z dx plus q dy, sorry, q is equal to x, plus y dz. And now you have x, y, and z, and you have dx, dy, dz, just in your limits, so just fill them all in. So from 0 to 1 in t, z is t squared, dx, so that's x prime, which is 2t, plus x, which is t squared, dy, which is 3t squared. So this is z dx plus x dy plus y dz. So that's t cubed, z prime is 2t dt. So then you can just condense it from there. So we have 2t cubed plus 3t to the 4th plus 2t cubed again. Wait. No, 2t to the 4th dt. And of course you can combine these two terms and then just integrate from there. So this is on page 115 in the notes where this is worked out. Okay, so that's all the examples I have about line integrals of vector fields, but we'll keep working with line integrals of vector fields into the next section. Oh, dang it. I forgot to take attendance. Okay, but I'm done, but please sign out before you leave. 6 people in this. Whoops, totally forgot to record that.